Alright, welcome back. So in this video I am talking about the second part of the fundamental theorem of calculus. Again, this is just what I think the second part is. I've seen it done both ways with the parts swapped orders, depending on which book you're looking at, or who you're talking to. So in this video, I'm just going to talk about the rule, the theorem itself, and give you the ways that it gets used when we do example problems. The intuition is going to be in other resources for you for why this is the way it is. Okay, so this is set up similar to how the first part of the fundamental theorem of calculus looked. We have a continuous function on an interval a to b, and we have big F of x, which is an antiderivative of little f. Then the integral from a to b of little f of x dx is equal to big F of b minus big F of a. So if we find an antiderivative, big F, we just substitute in those endpoints, b, and then we substitute in minus a, and that gives us the value of the integral. This is going to be really powerful for us. Before we get into that, I just want to mention that we use this bar notation, so it looks like f of x with a bar from a to b, to represent evaluating the big function f, so that's f of b minus f of a. That bar is just a way for us to write out what we're doing to keep track of it as we're doing the math through, and it's just an easier way to notate that we've taken the integral, we now have big F, and we're looking at it evaluated from a to b with that bar notation. So what does this fundamental theorem tell us? This means that evaluating a definite integral, the integral from a to b of f, is as simple as finding an antiderivative, and then evaluating it at the endpoints. I have simple in quotations here because a lot of this course is devoted to just how complicated it can be to find an antiderivative, but for now we're using sort of simple examples, and so it really is just as straightforward as finding an antiderivative and evaluating the endpoints. Okay, so the first part of the fundamental theorem of calculus tells us that differentiating and integrating are inverse operations, or so they undo each other. This tells us here that when we are evaluating a definite integral, all we need to do is find an antiderivative, and we can evaluate the endpoints and get the solution to the definite integral. Okay, so let's try this on an example. Let's evaluate the integral from 0 to 3 of x squared minus 5 dx. So remember, the definite integral finds the area under the curve. So if we could graph this and find the exact area under the curve, we could do that. But instead, what we can do now is just find an antiderivative and use that instead. So let's do that here. The antiderivative of x squared is 1/3 x cubed, and the antiderivative of negative 5 is 5x. So I'm getting 1/3 x cubed minus 5x as an antiderivative. And again, you can just check this in your brain really quick. You might be sort of fluent at taking derivatives by now, so you can take the derivative. I'm getting x squared minus 5, which is what I want. So this is an antiderivative, and we're evaluating it from 0 to 3. So I like to think of this bar kind of falling into the function. So we evaluate the top bound first, we evaluate at 3, and then we subtract what happens when we evaluate at 0. Okay, so put the 3 in for x. I'm getting 1/3 times 3 cubed minus 5 times 3, and I'm subtracting 1/3 times 0 cubed minus 5 times 0. So I'm plugging in 3, doing that, and then subtracting what happens when I plug in 0. So simplifying the first bit, I'm doing 3 cubed divided by 3. That's 27 divided by 3, which is 9. Then I'm subtracting 15. And the second term, all of that stuff with the zeros, is just 0. It's all being multiplied by zeros, so we're subtracting off 0. Then I have 9 minus 15, which is negative 6. And so this is telling me that the area under the curve, x squared minus 5, from 0 to 3, is equal to negative 6. Pretty cool. This is a good time to note that whenever you are doing a definite integral with bounds, your answer should be a number because you're finding an area. It shouldn't have any variables left in it. If it has variables, that means you haven't finished the problem yet. Okay, let's keep doing examples. So we're going to evaluate the integral from pi to 2 pi of sine x dx. So evaluating this is as simple as finding an antiderivative for sine. So the antiderivative of sine is negative cosine. That's because the derivative of cosine is negative sine, and we need to cancel it out. And we're going to evaluate negative cosine from pi to 2 pi. So first, the 2 pi gets plugged in. I'm doing negative cosine of 2 pi, and I'm subtracting off what happens when I substitute in pi, so I'm subtracting negative cosine of pi. Cosine of 2 pi is 1. Cosine of pi is negative 1. I've got lots of negatives going on there, just got to keep track of those. So 3 negatives is just still a negative, so I have negative 1 minus 1, which is negative 2. That's the area under the curve of sine from pi to 2 pi. Pretty cool. Okay, I'm just going to do 2 more examples. At this point, you should be seeing that really what we're doing is just evaluating antiderivatives. So finding antiderivatives is coming real in handy right now, and we're going to get lots of practice with it going forward. So next, let's evaluate the integral from negative 5 to 3 of e to the x dx. So the antiderivative of e to the x is just e to the x, and then I evaluate this from negative 5 to 3. So I'm going to have e's in my final answer. That's okay with me. I'm doing e to the 3rd power minus e to the negative 5 power. That's my f of b minus f of a. And that's my answer. There's no x's left over, so this is a number, a constant of some sort. And this is just the representation of the area under the curve e to the x from negative 5 to 3. Okay, it's nice when it's e to the x. Those ones aren't too bad. Let's do another one. So this is our last example. Let's evaluate the integral from 4 to 9 of square root of x dx. So I'm kind of assuming that antiderivatives aren't too difficult for you, but this still might be the beginning of your process in learning about antiderivatives. It might still be sort of something you're working on, just like when you were first learning how to take derivatives. So give yourself some patience and some kindness if it's taking you a second to remember how to do the antiderivatives. We continue to talk about antiderivatives for a long time in this course, especially when we talk about indefinite integrals. So you're going to get a lot of practice. Just bear with me as we're working through these, and I promise you'll get better as you keep doing more and more examples. Okay, so we're doing the integral from 4 to 9 of square root of x dx. In order to find the antiderivative of square root of x, I'm going to write it as x to the 1/2. So then this is something as x to a power. The antiderivative then is 1 divided by that power plus 1, so 1 over 1/2 plus 1, and then I add 1 to the exponent, so x to the 1/2 plus 1. So here, this is really 1 over 3/2 times x to the 3/2, and I'm evaluating it from 4 to 9 still. And to make this even simpler, I'm going to rewrite it. Multiplying by the reciprocal, I'm getting 2/3 times, and then x to the 3/2 is just the square root of x to the 3rd power. So I'm evaluating from 4 to 9. This kind of falls into the function. The 9 goes first, then we subtract off what happens with the 4. So I'm doing 2/3 times the square root of 9 cubed minus 2/3 times the square root of 4 cubed. Square root of 9 is 3, the square root of 4 is 2. Then I just have to simplify. So I'm getting 2/3 times 27 minus 2/3 times 8. That's 54 over 3 minus 16 over 3, which is 38 over 3. And that is my answer. So this is the area under the curve square root of x from 4 to 9. There we go. Okay, so fundamental theorem of calculus part 2 tells you that finding the definite integral is the same as finding an antiderivative and substituting in the endpoints, f of b minus f of a. So we'll be doing this a lot as we do more examples with definite integrals and as we do integrals more generally. That's it for this one. Thanks so much for watching, and I will talk to you in the next one.